Good afternoon. My name is Greg Johnson and I'm with Zeiss Microscopy. I'll be talking to you today about technique selection for front-ended line, defect localization, and bulk silicon. I'll be answering two questions. The first is why localize? The second is how to localize. Let's look at the first question. Consider a case study that might happen in the real world. Suppose you have a diode leakage array that's built up like an SRAM to test for leakages in a SRAM environment. The structure could have thousands of source drain contacts wired up in parallel. The test measures the reverse bias leakage from the source drain to the well, and multiple chip sites are failing. Here's a crude schematic showing basically what the test is doing. The proposed solution was scanning capacitance microscopy, which is a powerful technique for imaging junctions. One can scan an AFM tip across a cross-section. You measure the DC/dV at every pixel, and from that you can derive active dopant concentrations such as N+, P+, N-well, or P-well. On the right, a typical good region is shown where the brown areas are N-well, and we see nice regular pattern formations, and the yellow areas are P-well. The important question is, where would you cut? We know that the inline test can select the worst failing chip, and it's isolated to a 100 micron square block, but where do you cut? Where do you look? Perhaps we could ask our statisticians. You might cut horizontally and look in the center, cut vertically, look in the center, maybe on the edge vertically, or maybe order multiple sections. The problem with this approach is it can get very expensive as far as resources, especially with a technique like SCM that can be very time and resource intensive. Fortunately, we have a localization technique available to us called EBIC, optical beam induced resistance change. In this technique, we apply a bias, then we scan the backside with a 1340 nanometer laser, and we map the resistance change at each pixel. We can see here we're scanning along with our laser, and we measure the resistance at this pixel, and all the way across. At a healthy junction, you may have 1 degree of heating, which changes the resistivity and then is caught up in the resistance measurement. However, at a defect, there could be a large delta R due to different materials, different geometries, and so forth. And so the EBIC signal is a measure of the change in resistance as a function of temperature. Here are our results. This is a scan of the top right corner of an array. The white contrast is the EBIC signal. Let's look at what we can learn about the spot density. We can see from this image that it's concentrated along the top edge, and it's also sporadically along the right edge. Now, scanning capacitance microscopy characterization may analyze actual leakage spots and give you an intelligent answer as to exactly what's going on in your sample. That is why you localize. And here are the results. The image here on the right shows both a good region and also what you're likely to get if you just cut a random region. We have a nice regular array of wells, nicely formed. However, at one of our EBIC spots, we can see very carefully here, you can see the yellow being the P well or the P-type material. We have an area of over-doping of the diffusion implant. Thus, we learned that defect localization was able to find the exact spot of the leakage. Our next question is how to localize. The full version of this course will involve looking at 7 different localization techniques, and they are electron beam absorbed current, electron beam induced current, passive voltage contrast, electron beam induced resistance change, lock-in thermography, photon emission microscopy, and conductive atomic force microscopy. Let's define those. EBAC is current absorbed at a probe. EBIC is current due to internal electric fields. PVC is secondary electron yield differences. EBIC is resistance change in a circuit due to heating and or possible other beam interactions. LIT is the imaging of thermal radiation. PEM is the emission of photons from PN junctions. And CAFM are measurements with an AFM probe. In this shortened version, the 20-minute version of this talk, we'll only have time to look at the first three: EBAC, EBIC, and PVC. Our first technique is EBAC, electron beam absorbed current. This is, again, is defined as current absorbed at a probe. Consider you have a metal line with a break at an unknown location in its center. We'll apply a probe, which is essentially a needle attached to an op-amp amplifier. When we scan the sample with an electron beam, on the signal side, on this half of the defect, the electrons that are introduced to the sample or liberated from the sample, inside the sample, will be imaged in the system. That can be recorded in the system as a black or dark area. Whereas on the decoupled side, on the other side of the break, the electrons are lost to the sample and they become, it's essentially invisible as far as the imaging system is concerned. Here's an EBAC example, an opens test in a via daisy chain. In this inset image, we can follow the conductive path around, come out from our needle, we follow the bus lines around and into our sample. And here we can see, because of the design of this test structure, we've actually localized two different opens. So EBAC opens is very heavily used in via chain opens tests. It's also useful in device characterization. Here's a look at gate continuity, where we have a sample delayered down to contact level. On the left image, we have our SEM image, and we're touching down on a gate contact. In the right image, we see the EBAC response, and here the white area is the continuity, the areas that are contiguous with the electrically with the probe. And we note that what should be the gate doesn't extend all the way up here, so there might be something we would want to go investigate further. So we've analyzed the problem with a gate by means of EBAC. Our next example, EBAC is very heavily used in logic net tracing. You might have a question of what is electrically connected to this feature. You would drop a probe. And then, because it's a SEM-based technique, you could use different acceleration potentials or different beam landing energies to look deep into the sample. For example, at 2 kV, because the electron penetration depth is actually less than the subsurface wiring, a 2 kV image is only going to show us the top surface features. Whereas at 8 kV, we can see the beam will be interacting with the subsurface wiring, and therefore we can sometimes measure out the entire net. And there may be cases where you want to be able to see that. And other cases where you might have a sensitive sample where you only want to use the minimum energy possible. Our next technique is electron beam induced current, EBIC. That is defined as current due to internal electric fields. It may be helpful to review the properties of a junction. When you put a P and N-type material together, there's a charge imbalance due to the diffusion and drift currents reaching equilibrium. Because of that charge imbalance, there's a voltage, a built-in potential, and there's also an electric field at the area, the depletion zone, the area that's depleted of majority carriers. The thing that's important to note is for this technique is the electric field is 0 outside of the depletion zone. Consider a sample with a PN junction, and you have to remember, again, to remind the P+ side has no field, there's a high field at the depletion zone and a no field again at the N+ side. Now we drop a probe and we scan it with an SEM beam. And now we have we're dumping electrons into the sample. There may be three sources of electrons. One may be the incident beam, the other may be the secondaries that are generated, or the electron hole pairs that are liberated. All of them, because they see no electric field, may recombine or be reabsorbed and not contribute much to any kind of measurement up here. However, when we hit the depletion zone, the internal electric field, we can view that as like kicking electrons to the right, and this flow of current here is actually going to be measured as a current over at our op amp. And then when we get to the other side, again, not much happens. Any liberated electrons are reabsorbed, and so there's no EBIC signal. In so doing, EBIC creates images of depletion zones in semiconductors. It can be used to explore the hidden connectivity or monitor the health of PN junctions. Here's a case of a SEM image of one probe pad dropped on a 100 micron test pad. And we have our SEM image of a rather small chip over here. And at 5 kV, we're looking at EBIC. It's essentially just the EBAC, the connectivity of the hidden wiring. But then when we go to 20 kV, we can start to see different types of junction effects in different colors, showing that we're actually exploring the junctions and other internal electric fields deep in our sample. Here's a topic that's becoming of greater interest in advanced technology nodes is EBIC in cross-section. This sample is a chip that's been built with a test structure that's a diode test array. The chip has been cross-sectioned perpendicular to the wells. We have one probe dropped on an N+ diffusion test pad and one probe on the surface of the sample. Schematically, looking at what we're going to be showing you in a second, is it's a diode test structure with multiple N+ and P+ diffusions laid out in parallel with both an N well guard ring, as you might say, and a P well. Now, when we perform EBIC, we're imaging multiple kinds of depletion zones. The N+ P well, the N well P well, which is larger because of the effect of the lower carrier concentration. And we're even getting a fascinating result of some effect from the P+ P well depletion zone. So EBIC is a very powerful technique that can give you a lot of advanced characterization of diodes and junction properties in semiconductors. Here's another example where we have an SRAM that's been delayered down to contact level, and we've dropped one probe on an internal node right here. This is our SEM image. Now, when we do EBIC, we're seeing some fascinating results. We actually have a black signal here that is due to the PFET, the PRX, the P active line, and the N active lines are showing up as white. What's going on? Come to the full course. Our next technique is passive voltage contrast. This is defined as secondary electron yield differences. The outline of this PVC area is, we'll define it again, we'll look at beam sources and phenomena that lead to PVC. Definition is PVC is the difference in the detection yield of secondary electrons across different regions of a sample in response to scanning by a beam. Several different beams have been used. The SEM for electrons, also gallium and helium fib. Let's consider the types of PVC, the different mechanisms that can lead to PVC. The capacitance, grounding state, and the built-in potential of a PN junction. First, looking at capacitance. Let's say we have two lines. One that is a good non-defective case that is not shorted to a nearby feature, It has a smaller reservoir with a low capacitance. Then we have a line which is defective. It's shorted to a nearby buried feature. In this case, we have a bigger reservoir, a high capacitance. Now the SEM beam scans, creating secondary electrons wherever it goes. On the side without the defect, the initial loss of secondaries cause a positive charge buildup, and therefore subsequently fewer electrons escape, and therefore it is dark. Whereas on the shorted side, any electrons lost are replaced by the reservoir. More electrons escape, and therefore it's brighter. So the bright to dark contrast can highlight defects. And this is actually a technique that's widely used in industry today in full wafer voltage contrast inspection. Next technique is the grounding state. Consider we have a line with a break at an unknown location in its middle. And we can add a grounding tap either by the design of the test structure or by fib milling. Now let's consider both the floating and the grounding side. On the floating side, again, it will charge up due to the loss of secondaries. It'll charge up positive and therefore make it harder for electrons to escape and have lower secondary electron yield. It is dark. On the grounded side, the ground tap can resupply electrons and it will continue to emit and be bright. Therefore, at low magnification inspection, it's very easy to see the location of the break in the line. Now let's look at the built-in potential of a PN junction. As a reminder, this diagram we saw before, the important detail we want to look at now is the voltage. And you have to realize that against common intuition perhaps, the P side is negative and the N side is positive across the whole side of this area. Now if we have a junction, a PN junction, when the beam scans, it's going to create secondary electrons. On the P side, because it's negative, more secondaries can escape the negative surface. On the N side, fewer secondaries escape the positive surface. And in so doing, this concept where healthy P diodes or P sides are bright and N sides are dark, we have a lot of different voltage contrast techniques used in inspection for diodes. Here's a healthy area that happens to be examined by a gallium fib, where the P plus contacts are bright, the NRX contacts are medium dark, and the pass gate, the gate contacts are very dark because they are completely floating. Here's an example of finding actual defects. The defect should be bright, but we're not actually missing a contact here. It is just completely dark because it's only partially filled. And over here on the NFET side, we have a row of NFET contacts that should be dark, but they're bright because of a short of the silicide into the channel. Here's a more complicated concept. We're looking at samples that have been in plan view. And we have a chip that's been polished to below the gate, actually very deep. So there's only a very slight oxide remaining above the wells of the sample, the bare silicon, you might say. Look at it in a gallium fib, and we have a beautiful image of the delineation between the N wells and the N side and the P side, the N well and the P well. This is a planarized top-down view where we polish down to this level in the silicon. And now, consider we go take another sample and only polish it very shallow, just barely underneath the gates. And now we'll compare gallium to helium voltage contrast. Again, so this is an SRAM viewed just under the gate, just barely polished to remove the gate. And now we can see that the helium voltage contrast shows a very superior PVC. Because of the different beam physics, you can do some modeling in Casino or SRIM to look at the different beam interactions with your sample, and that can help you decide what technique you might want to use, whether what what beam landing energy in a SEM, or if you have advanced fibs available to you, what you might want to look at. Our full talk will cover 7 different localization techniques. And there are 4 of them that we're skipping over today, but let's just show an interesting teaser image from each concept. In EBIC, we can actually look at a particular device when it's turned on. This is the on current of a pull-down device examined in EBIC. And we can actually see both the contacts and even a thermal effect of an unused gate. That's EBIC. The next concept we'll be going in greater detail is lock-in thermography. And one of the key features is that it allows you to see through, you have almost X-ray vision right through metal plates. And here's a case where we've localized a defect looking through a metal plate, whereas the cross-section shows our defect. The next concept is photon emission. We have various different cameras available to us, InGas or CCD, and they have different wavelengths of sensitivity. And here's a case of looking at good and bad samples in a ring oscillator, where we can see the different patterns and identify defects on bad chips. Conductive AFM, we have a new module this year. We'll be talking about conductive AFM in the SEM itself. And here's just a quick view of an SRAM array where we've got color coding, where we applied different voltages on the back side of the chip, and we can either highlight PFETs or NFETs, and thereby see when any contact has the junction problem with a quick scan of the whole area. And with that, I'd like to thank you. I hope to see you in Pasadena, where we'll have a full discussion of 7 different localization techniques. And thank you and good day.